Hey guys, Mr. McKinney here, just finishing up our Unit 5 review session. So I just wanted to go over what the first and second derivative will help you figure out about the original function and how they're related to each other. So I created this nice little summary page. I would copy this into your notes. This is a very useful reference to help you figure out what the derivatives tell you about the original function and kind of what they tell you about each other. So let's look at the first derivative first. So f prime. Another way of thinking about the first derivative is that it's either the slope of f or the rate of change of f. That's just the definition of what the derivative is. If the derivative is positive, that means the original function is increasing. If the derivative is negative, that means the original function is decreasing. And the first derivative can help you find local maxes and local mins. And a local max would happen if f prime goes from positive to negative. If we go from increasing to decreasing, we're at the top. A local min happens if f prime goes from negative to positive. So if we go from decreasing to increasing, we're at a local minimum. So the first derivative will help you answer questions about slope, will help you answer questions about when f is increasing and decreasing, and will help you answer questions about local maxes and mins. These might also be your absolute maxes and mins. You would also need to check the endpoints. The second derivative, so again, that's just the derivative of the first derivative, so f double prime of x. So that's the rate of change of the rate of change of f. Another way to think about that is that the second derivative is just the rate of change of f prime. So it's the slope of f, or it's the slope of f prime. Basically, the second derivative tells you how the first derivative is changing, the rate of change of the first derivative. Now, the second derivative will help you answer questions about concavity on the original function. So if the second derivative is positive, the original function is concave up, so it looks like that. If the second derivative is negative, the original function is concave down. So again, concave up, concave down. Notice that you can have negative slope or positive slope in each case because the second derivative doesn't tell you if the slope is positive or negative. The second derivative tells you if the slope is increasing or decreasing. It's telling you how the slope is changing. So if the second derivative is positive, we're increasing f prime. So f prime is increasing when the second derivative is positive. So the slope is going from negative to 0 to positive. And if f double prime is negative, that means the original function is concave down, which also means that the slope is decreasing. So we'd go from positive slope to 0 slope to negative slope. A second derivative can also help you find points of inflection. So if f double prime goes from positive to negative, or if it goes from negative to positive, then you'd have a point of inflection. And the function would need to be continuous at that point. All right, so this was a summary page that's already been in our notes. Basically, this is how to find extrema and concavity. Extrema is basically just talking about maxes and mins. And when we're talking about local maxes and mins, that's going to happen at your critical points, which is when the first derivative is 0 undefined. I really just wish, instead of critical points, I wish we called them possible extrema or possible extrema locations. But they came up with another word, and this will pop up on the AP exam. So a critical value or a critical point refers to when f prime of x is 0 or undefined. If f prime actually switches from positive to negative or negative to positive, then we have a local max or min. The second derivative helps you answer questions about whether the original function is concave up or concave down. It can also help you find points of inflection. So possible points of inflection happen when the second derivative is 0 undefined. The actual point of inflection happens if we change sign on either side there. So positive to negative or negative to positive. The rest of this unit was just on optimization, which was basically just word problems. Now, keep in mind that we're trying to either maximize or minimize something. So we're going to be using our first derivative because we're going to be looking for extrema, either maxes or mins. We've already done all these word problems, so I'm not going to set them up again. I'm just going to kind of talk about what's going on in these problems. So Mr. Jansen's has some sound effects in his slideshow. So he just chopped off the top of the box. So if we had our 8-foot piece of metal and we're cutting out corners, the volume would be length times width times height. And I know I need a volume equation because I'm trying to maximize volume. So I'm going to look at when V prime is 0 and when it goes from positive to negative, or potentially at the endpoints. Now, the way you set this up, it's going to go up a distance of x, because we're cutting out x from the corners, and then the length and the width are both going to be 8 minus 2x, because you've cut out the x from each corner. So you'd say 8 minus 2x times 8 minus 2x times x. We want to maximize the volume. Now, basically, the domain for this one would be going from 0 to 4, because you could cut out 0 inches or you could cut out 4 inches. If you try to cut out more than 4, you've cut out the whole thing. I would multiply this out before you try to take the derivative, otherwise you have to use the product rule a whole bunch. Minimum perimeter, and it gives you area. So we know we're going to need both these formulas. Area, and let's draw a picture of a rectangle, x times y. Area would be x times y. Perimeter would be 2x plus 2y. Since I want to minimize perimeter, I know I want p prime to equal 0, and p prime should go from negative to positive. The reason I set up the area equation is because they give me the area. So I can say 81 equals x times y, and then solve for either of these and plug it in over here. It really doesn't matter because everything's set up the same. So y equals 81 over x, plug that in over here, so 2x plus 2 times 81 over x. Simplify this and then take the derivative. Then set up your table and look for where p prime goes from negative to positive. This last one was super duper tricky, but again, we're trying to maximize area, and then we've got the hypotenuse. So we know we're dealing with the right triangle. A, B, C. Area would be 1/2 times A times B. And then it gives us the hypotenuse, so we know that a squared plus b squared equals c squared, except I know that c is 5. So I can say a squared plus b squared equals 25. 5 squared is 25. A squared would be 25 minus b squared, so a would be the root here. And then I can plug that in here. Now I have this equation in terms of b, and then I can take the derivative. If I want maximum area, a prime should be 0, and a prime should go from positive to negative. These videos were already recorded, so if you want all the way worked out, just go back and rewatch them. Hope this was helpful. Good luck on the test after Thanksgiving break.